What's up, YouTube? In this video, we're going to be looking at benchmarking. Benchmarking as a concept and BenchmarkDotNet as a tool to help with benchmarking. Now, this is going to be, in some cases, very intense with regards to if you're not familiar with benchmarking. But I want to show you more about the tool. It's not going to be an in-depth review or training on the tool itself. I'm going to get you started. I'll talk about some of the things you need to be careful of. I'll talk about what BenchmarkDotNet doesn't do, and some of the controls you have available to you. But it is by no means a full-on BenchmarkDotNet tutorial. But I think people should know how to use these things, and you never know where you use BenchmarkDotNet for finding out whether your theory or assumptions or hypotheses are correct. And I do that actually quite a bit as well. So for example, do you know if string is if the equals operator is faster than the equals method? No? Well, then find out. Or there have been times where I'm working on some sort of a algorithm, just to keep it simple. Let's say I'm parsing some strings. And as I'm building out the first cut, if you will, I have certain hypotheses about, if I did this and I did that, I might improve performance and or might, whatever. So what I do in a situation like that is, especially if something is really critical to the business function, I will have the first cut, what I call the baseline, and I will benchmark it. I'll have a bunch of unit tests I'll write for that, the functionality, because if I make changes, I want to make sure that the changed versions are conforming to the requirement, and then I can benchmark it separately to see if it's becoming better or worse from the baseline. So benchmarking is certainly a good tool for that sort of thing. But don't confuse profiling with benchmarking. Profiling and benchmarking are two very different things. Profiling is when typically profiling is dynamic, meaning you're doing this at runtime in your application. Let's say you have a button on your web page that's very important, and when the customer clicks the button, you expect it to take, 100 milliseconds, and it takes a second. And you think, what the heck's going on here? So you're going to attach a profile, and the profile is going to give you a lot of information, such as what methods were called when that one button was clicked, and how long did the execution spend in each method, and how many times was each method called, and so on and so forth. With profiling, you can build, let's say, a hypothesis about where you might look to fix a problem. Or maybe, you're calling a method more times than you should be. Like, why is it calling this method, 1 million times? So the profiler will give you information that may surprise you or may at least guide you with regards to what's the direction you should head at. And of course, if you're, let's say this, in this call chain after this button click, you are saying, well, if that method is being called, 1,000 times, then what if I could just optimize that method just a little bit? And that could get you huge performance gains because it's being called so many times. So profiling is going to give you information like that. It's not going to tell you, it's not going to help you do the diagnostics on how to improve performance, but it's going to tell you what's happening. Now, you can certainly use profiling to see if you're improving performance. Certainly, that's another use of a profiler. Benchmarking is more to do with testing out time of a certain method typically, or a certain operation that by calling one method, a bunch of things happen. How long does that take? And then by tweaking your code or doing some optimizations to see if those optimizations are improving in the direction, at least in which you want to head. And there's many cases. In fact, there's one case we'll probably talk about today, building a URL slug producer. A URL slug is essentially, you see this on Stack Overflow and other blog sites where the title of the question or the title of the blog becomes the URL for that blog, or the tail end of the URL. But your title might contain certain URL invalid characters, and so the slug producer has to look at the title and then do the magic to make sure that the URL does not contain URL invalid characters and replace them with underscores or something, dashes or whatever. So it's simple, but yet it's fairly complicated. So when I wrote one of these for one of my blogs, I had the simple implementation. This was many years ago. And once I had that done and I had a bunch of tests to test out the rest of the system, I said, okay, now that I have all these tests, let me see if I can optimize this slug producer. So I came up with a version 2, if you will, implementation of the parsing logic in there. So yeah, this is definitely faster, because you spend a lot of time trying to optimize it, and you think is, given everything you know about .NET or the platform, it's going to be faster. Bad idea. Don't trust just your ideas and assumptions. Make sure you can validate that. And so that's where benchmarking can come in handy. You have a hypothesis, you want to prove out that hypothesis, you use benchmarking to ensure that your hypothesis is not just a hypothesis. It's a fact. So it turns out years later, BenchmarkDotNet came about, and I said, hey, this is a good tool for me to see if I was correct, 4 or 5 years ago. And I was wrong. So I said, okay, then let me build another implementation to see if, I'm any faster. And sure enough, then with the help of BenchmarkDotNet, I was able to write another parsing routine for the same thing. And of course, I had the test to validate that I'm doing the output is the same. I was able to implement something that was faster. Now, did it matter for that specific scenario? Of course it didn't, but I was using BenchmarkDotNet for the first time. I was excited to have such a tool, and I used it for that. And yes, and since then I used it for all kinds of things in production code, but certainly even the question like I asked you in the beginning, is there a difference in performance between the equals operator and the equals method, let's say for strings? I'll use BenchmarkDotNet to find out. Anyway, so what I'm going to do now, I'm going to start with getting you started. And as we're getting started, it'll be a very simple application, obviously, because of the fact that we're getting started. Walk you through some of the things to look at and understand. And then I'm going to show you a bunch of code that I've written to benchmark various things. I don't think we'll get through all of them, but I'll make the code available in the show notes below, and you can take a look at them when you get the time. Hopefully you get the time. I'm gonna have a sip of coffee here. Somebody didn't let me have my coffee this morning. So to get started, you're going to need to use BenchmarkDotNet, the NuGet. Okay. So I'm going to go into my NuGet package manager, and I'm going to browse for BenchmarkDotNet. And see the spelling is BenchmarkDotNet spelled out. And the website is guess what it is? BenchmarkDotNet.com. BenchmarkDotNet.com. Okay, now in the .NET Core, and this, don't use the .NET Core version. It's, even though your project may be a .NET Core, this has been deprecated. Yes, you can see it's been deprecated. Just use this one, even though it says .NET, it's for both platforms or all .NET platforms. Once you install that, your next step is to build a benchmarking application. So the trick is, this is just a standard console application. This is a .NET Core application. And the way you get started is this. First of all, you'd say benchmark runner.run, and benchmark runner's namespace has to be included in here. Okay, now what run takes is it takes a class name. So I'm going to provide it with program here in this case. But you're not limited to one class. I mean, yeah, you can, this class, you can actually call out other classes, which is typically if you're writing a play application, meaning you're just trying to test a little theory, then this is fine. If you're intending to maintain those applications as part of, let's call it production, then I would suggest just defining separate classes for the different kinds of benchmarks you're doing. And then from here, you can just call one of those classes. Now they have a switcher. I'm getting ahead of myself. So let's just stick with the simple parts, and I'll go into the details. So I have this, I'm giving the same class as the runner. Classes have to be public for BenchmarkDotNet to be able to find them and use them. And all methods need to be, it's not static, it's not required, but it's a good idea to have it static since the whole class is static anyways. All methods you want to have benchmarked also need to be static. And these methods can return a void or nothing. Actually, I'm right, because void is not nothing. Void is a type in .NET. So yeah, so you can return void or nothing. No, so you can return void or something, but the recommendation is to return something always from these benchmark methods, because otherwise the jitter might optimize your code. You just can't, these days, you can't second guess the jitter. You can't imagine what it's going to do, and it's changing all the time. So my suggestion would be just return something. So let's say we're going to return something. And I'm going to implement this, or the burning question we have, remember the equals operator versus the equals method. So I'm going to call this method equals operator. And this method needs to be decorated with the benchmark benchmark attribute. And that's another using for the attributes. And here, let's say, so simplistically speaking, this is what I'm trying to do. I'm going to say return. Something like that. So there needs to be a bool. What did I say? It's returning a string. All right. Now, of course, this is not how we want to do this. So I'm going to define local variables here. And these variables can be private, but they need to be static. And this is a string. And let's call it value1 and value2. I will have to set these value1s and value2 somehow, but then over here, we're just going to say is value1 equal to value2. Right? So conceptually, there's no problem here. Now you might want to have a burning question as to, but that's just one value. I'll get to those things, right? I'll show you various ways you can do this. So why is it not liking this? So it's saying static types cannot be used. Okay, so this class can't be static. My mistake. The methods are static, but the class can't be marked as static. And then we have, let's say in the main, we can say this value1 is equal to something, value2 is equal to something. Now in BenchmarkDotNet, they have various other attributes you can use, where one of them is called global setup. There's a ton of attributes. What global setup does, global setup, and I'm just going to call this, it has to be public again, public void. I'll just call it initialize, even though I typically would call it setup. Let me call it setup. My other projects I actually call it analyze, initialize. So in the setup, I can say value1 is equal to something, and value2 is equal to something else, or it could be something, doesn't matter. So essentially, this is where we're trying to get to. So now what's going to happen is, again, we are coming sort of back to square one, which is, but what if we want to change the value different times? And sometimes they're equal, sometimes they're not, so you can get that sense. So in essence, you're trying to parameterize your benchmarks, which is a valid use case. So towards that end, what we need to do is, let's say we have an array. I'm going to keep it simple here. In the real world, it gets a little more involved in the projects that I make available to you on my GitHub. It's quite an involved, but conceptually it's the same idea. So let's say I have a private static, and since everything is private, I'm not sure why I'm making these static. And then everything is not, well, main is static, yeah, so I might have to do that for, no. Basically, the class cannot be static, and nothing can be static that is being used. So even your methods cannot be static. The benchmark methods cannot be static, but main is static, so which is fine. So here, let's say I have a string array. Let's call it data1, and it's equal to all right. So that's 4. And data2, Let's say the first one's equal, the next one is not, this one's not, and last one's equal. And so we have these two arrays with 4 values each. Idea being that somehow we need to magically be able to set value 1 and value 2 to each of these elements here. So we are going to use another property. Let's call it the index. So this will also have to be private. And I'll explain why all of this is, sorry, public, I mean. And this, we'll call this index. And this will be, needs to be a get set property. Can't just be a get, even though we just want to do a get. Okay. So in this setup now, so this main is done, we're over and done with. We don't quite need it besides setting up the run part here. Our setup is going to do the setup. And I'll explain when and how many times this is going to run. So value 1, I want this to be the data 1 of index. And this all makes sense eventually once I finish with the code and we run the app a little bit. Data 2.index, or not dot index, but index of data 2. All right, and I'll have a separate, another method here for benchmarking. And we'll call it, this is the equals operator and the equals method. And here we'll use the method. Equals. All right. So now let's say we want to mark this benchmark. No, I'll get to that slowly. I'm sort of jumping ahead of myself again. Okay, so we're going to run this. Now you can't run these applications in debug mode. Why? Well, because in debug mode, there are no optimizations. And so BenchmarkDotNet is kind of helping you out here saying, well, you know that there are going to be some optimizations in release mode, so you can't run these in debug mode to get some sort of a sensible result. So it forces you to run this in debug mode. As a result, you're not able to debug your applications themselves, your benchmark applications. So that may be a bit of a hindrance in some situations. So I'm going to flip this to release mode, and I'm going to control F5 to run. You can't debug either, right? It's release mode. And there's a few things you're going to see up front. It says found 2 benchmarks, total of blah, blah, blah. So right now it's just, and I'll explain to you here. Actually, let me, I'm going to let this run here a little bit. And as we go forward, I'm not going to show you the whole running part. I'll fast forward the whole thing, but the first few things, in the first few times, I'm going to show you the details so you understand what's going on, and then for later tests, I'll skip through that process. All right, okay. So I'm just going to wait for this to finish. No, you don't want to wait. So, only I should wait. You want to just go on and do your thing. Okay, so the output is showing up here. I'm also going to show you that it has produced in your subfolder here. It'll actually be under release. It's produced this subfolder for BenchmarkDotNet artifacts, and in here it has this text file. So I'm going to use this text file to show you what's been going on, because it's essentially everything I put out on the console application in the console, it is also printed out over here. So it says found 2 benchmarks in total, blah, 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 and it's doing a bunch of things. Now, the first thing it does is it starts to JIT compile. Well, it's not doing it, but it's attempting to run your application. So it's going to get JIT compiled. It then measures the overhead that the JIT compilation took. Now, the JIT compilation, you might say that, how many times do you need to run the JIT? But it finds the best, it determines the best number of times to run all these things, because there's lots of optimization, especially in ReviewJIT, the new JIT compiler and tiered compilation. running the jitter once or twice may not be enough. So it determines what it needs to do, and then based on that, it determines how many times to run the JIT just to get a sense of what the overhead is and warm it up and that sort of thing. So that's doing the overhead, and then that's doing the workload. It's just run it one time. It is counting all the stuff, the overhead versus stuff, so it knows how much time to subtract from the actual time for the benchmark itself to run. It's very, very smart, this thing. And then it looks at the pilot, and in the pilot is trying to determine how many times should that benchmark itself run. How many iterations should it run? So they call it, what's the term they use? Invocations. How many times should it be invoked, that one benchmark method, to get a true sense, right? I mean, this one method takes nanoseconds. Like, how many times should I run it to get a good sense of how long it actually takes, you know? And so it's doing that here. The first time it says it tries 16, then it goes to 32, 64, and so on and so forth. And eventually it says, you know what, I need to run it so many times to get some real sense out of that. And then it divides that number and says, okay, this average, this thing, it took 2.3 nanoseconds. If you don't know what a nanosecond is, it's 10 to the power minus 9 seconds. So there's milli minus 3 seconds, 10 to the power minus 3, micro is 10 to the power minus 6, and nano is 10 to the power minus 9. And that is just the pilot. So once it's figured out how many times to run it, it then warms up the application again, because the .NET applications are JIT compiled, there's GCs involved, and the GCs they're smart. Our GC, the .NET GC, is smart in that it starts to optimize things. It starts to figure out, depending on how you're running this application, it starts to determine how much to allocate for Gen 0, Gen 1, Gen 2. And so just running it once is not enough. So the warm-up phase is doing all of that and getting the GC to figure out, like, you know, how much time, how to configure itself, and then actually do the run. Right? So that's the warm-up. Is then looking at its own overhead. The .NET BenchmarkDotNet itself has some overhead, so it's looking at its overhead, and so eventually the net result that it's going to show you is going to be the total minus its overhead is the actual number. So it's essentially what I'm trying to get across to you is handling all the things that you don't need to be worried about, but certainly you need to understand what's going on. And notice it's running it so many times. And then these are the number of invocations, 15 invocations. Each invocation is so many operations, so many times it's called that method, the benchmark method. And then it divides that number to give you the runtime. And this is the workload warm-up now. So this is, again, starting up the actual benchmark application, the benchmarked method. And then the actual, right? So it's still running it so many times, but this time it's decided it's going to run it 15 invocations. And so on. So now the way to look at this is in BenchmarkDotNet. Oops, let me lock my chair. In BenchmarkDotNet, there's a host application. So when you set up BenchmarkDotNet in your applications, there's a host application that runs. The host application then extracts out the one benchmark method that you have in the sense that it doesn't really extract it out, but it produces a child process. And the reason is that the child process is going to get its own, in its own app domain. It's got its own GC, jitter, the whole thing. And for every time it picks up a certain benchmark method, it is in its own child process. And then it does the overhead, the warm up, and all of that sort of thing. So now that child process is perfectly primed to start running the benchmark for the one benchmark method. And then it calls that so many times, 2, 6, 8, whatever times. For the next benchmark method that you might have in your benchmark tests is going to spawn another child process for that benchmark, and so on. So every benchmark method is spawned into a whole new process so that they each start from a clean slate, and the GC and other jitters and everything else will be compiling the code and it themselves as per that benchmark method and not the previous one. Right? So it's a fair test in that sense. Understanding how the .NET framework works, how the jitter works, BenchmarkDotNet has made its operations fairly automatic for you, so you don't have to know how to do all this stuff. It just does it, but you're going to see a lot of gobbledygook on your console. So I was trying to explain that to you. Now there are ways in which you can customize it. So you could say, hey, how does this method run on .NET Core versus .NET Framework versus Mono versus Core RT and so on and so forth. So you can configure it to run that same method or those same methods in different platforms to see the differences across platforms too. And there are differences across platforms, but it doesn't matter to you what platform, or you don't have a choice. But if it's okay. But if you needed to, you can control all of these things by way of either command line arguments or attributes. So there's a bunch of things that are available to you. But now, so if you understand the precursor that you're seeing here, so I go back to the console application, you're going to see, whoops, did I just close the console application? I guess I did. All right, so I'm just going to run through the console application in here. And I'm going to skip through all of that. So here are the results. As you can see, the equals operator method took 0.8 nanoseconds and the equals method took 0.4 nanoseconds, approximately half the time. But that's nanoseconds. That's like 1/2 of a nanosecond. It's just not a whole lot of time to worry about. But if you didn't know this already, then you got to look at the source code, the C# source code. You can look at the strings implementation for the equals operator and the equals method, and you will see that the equals operator method, the operator overloading is also in the form of a method or whatever they call it in C#, calls the equals method. So therefore, the equals method is faster because it doesn't have to make that additional method call. Method calls take time? Of course they do. They take time, of course, in the form of nanoseconds. But yes, it could build up. And there are many times where I shouldn't tell you this. I've done a few tests in the past without BenchmarkDotNet, but just generally when I've written the entire application in one single method. And that system just flies as compared to the normal design. But listen, if you're looking for that kind of performance, I had a need in this specific case. But if you're looking for that kind of performance, you're probably using the wrong tool, right? C# is not the language of the platform, or any managed language is not the platform to be using. Maybe you should be doing this in C or C++. I'm just saying. Method calls, objects, they all cost us some. The benefit we get is the abstraction that helps us understand what the system is doing, right? If you wrote it all in this one method and just jungle of code there, then maintainability just goes out the window, like literally out of this window here. Yeah. Okay. So now let's try and parameterize this thing. This was the simple run, and remember it's run two benchmarks. Now let's parameterize it and see how we do that, and then what that's going to do for us on the output, right? Okay, so to this index property, I'm going to decorate it with another attribute called params. And in this case, I could just type in, it could be a string or a data type, whatever. So I'm just going to say 0, 1, 2, 3, 4. These are the indices, if you will, for each of these elements. So here's when the magic starts to happen from a BenchmarkDotNet perspective. This global setup method is going to be running each time it runs before the benchmark method itself, but it'll run the global and the benchmark so many times. So it was running it 2 times before because we have 2 methods. Now it's going to run it 2 times 5. So it's going to now run 10 benchmarks, of which 5 are for one method, 5 are for the other method. And for every time it runs the global setup, each time it spins up that new process, the global sort of the pointer for the params will sort of change by 1, right? And so it'll start with 0. This index here will be 0. The next time it runs it with 1, then it runs it with 2, then it runs it with 3, runs it with 4, and so on. So this is one of the features you have in BenchmarkDotNet where you can sort of parameterize things. They also have attributes to set up methods to run before every test. There's a whole host of attributes that you can use, but global setup, and there's a global teardown and so on. So corresponding methods. So now because we've marked this property with the params and we've provided the values 0, 1, 2, 3, 4. And of course, you have to make sure in our case that the number of data elements and the number of indices here is the same. what's going to happen now is going to run each of these benchmarks with the value of AA, then BZ, CX, and DD, right? So when I run it this time, it's going to say it found 10 benchmarks, right? So it found 10 benchmarks here. And it's going to do this whole thing. So this is going to take a while. So sit back, go get a coffee. I'm going to have my coffee, and I'll see you when this thing is done. Deal? All right, stay right there, because like in no time it's going to happen. 1, 2. All right, so now we see another column here, the index, which is telling us the value of the index property that we have, which is, it starts with 0. So these 2 are for the 0, the 1, 2, and so on. And you can see that for when things are not equal, it takes a little longer. And then when they're equal, they take a little less time. So in some senses, this benchmark was a valid test. But designing a benchmark is not easy. It's just not. You got to think about so many things when you're designing a benchmark to ensure you're testing or truly testing what it is you're trying to test, right? In this case, we kind of lucked out with the, equals, some values that are equal and some values that are not. And we kind of made it half and half, but in reality, that's not the case. So in my benchmark methods or benchmarks, I use a randomizer, and I'll make that available to you in my source code that allows me to randomize various kinds of things. Of course, the implementations will be specific to the projects that it's being used in, but you'll get a sense of how to use that randomizer for these kinds of tests as well as for your unit tests if you need them for other purposes. So and we see the mean, the errors, and the standard deviation. One of the things that the benchmark stuff does is it removes outliers. So it found certain outliers which could potentially skew your results. Outliers are, let's say something kicks in on a machine, and that just causes the time to kind of go out of whack. So rather than skew the entire result, it says, okay, these are outliers, I'm just going to skip those. The guy that wrote BenchmarkDotNet, it has a PhD in mathematics. So he's very into statistics and various other things. I'm not a statistician. I've worked with many statisticians, and it's not my cup of tea. But if you understand statistics, then besides standard deviation and mean, they have a bunch of other features you can turn on and look at that might clue you in onto certain things. But a lot of the stuff, the default implementations takes care of a lot of the stuff for you. The other stuff can be if you want to customize things, you can do that as well. So this is the second feature, the parameterization of the benchmarks. And one more feature is the diagnosers. So you can look at memory diagnoser, and there's a bunch of diagnosers as well. The memory diagnoser is going to tell you for that benchmark how many Gen 0, Gen 1, Gen 2 collections occurred, so you can get a sense of how much memory was utilized and how many garbage collections occurred during a certain number of runs. Typically, it's per 1,000 runs, the output that they give you. And why is memory important? Well, because there's a tension between, tension, like once. So the tension is that sometimes to get better performance, your memory utilization starts to go up, and then you're having to decide between, can I allocate so much of memory to get this performance or not? Right? In a larger application, that may not be feasible. You can't just have an unbounded usage of memory. So the benchmark is going to tell you that this operation is faster, but it probably utilized more memory. Or you can say it's neck and neck, but this one method is using or allocating less memory, therefore less garbage collections, and so you might want to pick that. So that's an important aspect to look at in your benchmarks as well. The memory diagnoser will help you do that. But as I said, there are many, many diagnoses available. You can look at the documentation for those and determine whether you want to use those or not. Now, by default, it also writes out to that text file that I showed you in this folder. It's under this, it's a subfolder of the release folder called BenchmarkDotNet artifacts. And it produces a log file for each run, which is really the output from the console. You can export to CSV files. You can export it to rplot. R is a statistical tool that I've used in the past, but I don't like to install on my machine, so I don't have it here. But it gives you then graphing and charting features out of the box once you have R installed, and you turn on the rplot diagnoser. It'll just spin up the graphs, beautiful graphs for you. So if that's what you want, you have that option too. Or you can pull in the data into Excel and then build your own graphs with Excel's charting features. Okay, so I think that sort of, for the most part, covers getting started with BenchmarkDotNet and some of the features that I think are important for you to know going in. Now we're going to look at some other projects. So I'm going to shut down this thing and turn on my other project. So here's this project. I have a bunch of benchmarks I've set up in this project. And these are all by way of separate classes, right? Now, I've not used it here, but this sort of feature where I'm sort of turning on one and the other benchmark like this. When I'm done with this one, I'll comment this out and then I'll uncomment this out. This, of course, is the poor man's way of doing it. BenchmarkDotNet has, I think it's a third party, I'm not sure. Maybe it's part of the tooling called the switcher. Essentially, you can give it the assembly and it'll figure out all the benchmarks you have in there. And then it produces in the console, it produces like a choice menu. You can pick 0 for this, 1 for that, 2 for this, and so on and so forth. So you can, instead of doing it like this, you can use the switcher, and the switcher just basically makes that simple for you. So you can decide, what to run. But here's a thing where, let's say we have in this benchmark, I'm trying to do the array to dictionary value type benchmark. So let me turn this on. Let me show you this. So the question that I'm trying to answer with this benchmark is, is an array faster than a dictionary? Okay, here's what I'm going to do. You guys, before I show you the results, you guys are going to write down in the comment what you thought. Which was going to be faster. And I'm going to explain the problem, but then I want you to do that before the rest of the video, before you watch the rest of the video. So the idea is this. I've got an array of ints. These are value type. So it's an array of ints, even though the ints are all heap allocated. But the current content of the array is, did I say heaps are all heap allocated? Did I say arrays are? Arrays are all heap allocated. In this case, the array is of an int, which is a value type. And then there's a dictionary of value type as well. And the idea is, given a certain number of elements in an array, can the array find a specific element faster than a dictionary? What do you think? Okay, think about it and write your answer in the comments, and then you can find out for yourselves. I have a video that I've talked about. There's 2 videos on performance and memory allocations on my channel. I'll put links up to both of them here. Those 2 videos, they're separate from BenchmarkDotNet, but unfortunately or fortunately, performance also involves understanding the hardware and some of the things that might occur at hardware level that will impact your application. So you might want to look at those videos. If you're into performance tuning, they go hand in hand. You cannot imagine performance unless you actually understand how the hardware works. So take a look at those videos as well as over here. So what I've done is I've got one array that's an int. One is what I'm going to call a sorted array, and there's one the dictionary. And then there's the numbers to look up. I'll explain all this stuff. And then I got the parameterization of the number of elements in the array. So I start with 55 elements and then 80 elements, right? In the global setup, I use my randomizer to generate a bunch of ints. So I've got a random unique ints based on the number of elements. So now you know how this property is going to work, because the params is going to start with 55 elements and then it's going to become 60, 65 and so on. And once I have this int array populated with the random elements, I then have to sort these same elements. So I'm going to use the same exact elements and I'm going to sort them and put them into this dictionary, right? So that's really what I've done here. I don't mean dictionary, the array, the sorted array. And then I'm going to do the same thing for the dictionary. I'm going to iterate over the elements I have in here, and I'm going to insert them into the dictionary as well. So essentially the int array has a certain number of ints in there in a certain order, random order. The int sorted array is got the same numbers, but sorted. And then the dictionary has the same numbers in the same order as the int array has, all right? This is what I mean by design. You got to design things correctly to ensure you're testing the right things, because you're going to get a number, but maybe it's a false positive or a false negative, as the case may be. So you can't bank on a number if you design the benchmark itself, correctly. And then how do you look up the number? I mean, of course you have to know the numbers, but are you going to look up the numbers in the same order in which you insert them or what? So to do that, I then shuffle the int arrays numbers to come up with another array that has been further shuffled, if you will, from the original, but it's the same set of numbers. Okay, so you get that, right? Okay. And then I marked this method with the benchmark. In this case, it's the baseline, and I haven't explained the baseline. Essentially, of all the benchmarks that you have in your class here, one of them can be marked as the baseline equals true, and all other numbers for the other benchmarks will be in context or in relationship to this baseline. So there'll be another column added on, the ratio column, that will show you a ratio. So the output of this test will always be a 1. And all of the other tests will be either greater than or less than a 1 to let you know instantly whether something is faster or slower, or is it like twice as fast, half as slow, whatever the case may be, through the ratios. Now I'm also returning some value here, as you can tell. And I'm iterating over the numbers to look up, which was the shuffled collection. And in this case, I'm using the array, and I'm literally just iterating over the array to see if the number is the number I'm looking for. So it's an ON operation, right? Arrays. Searching for an element in an array is an ON operation. If the n becomes larger, the O becomes larger. For a dictionary, it's an O1 operation, right? And in a sorted array, it's a O log n. I forget what it is, but it's not as bad as a ON. And it's fairly decent number. All right, so that's the first benchmark. The next benchmark is for the sorted array. So I'm using the sorted array to do a binary search, and that's a feature in the .NET. You might have figured that out, right? Why is this guy sorting the array? Like, how's that going to help? Actually, there's another test we should look at on the branch prediction, which is another interesting one, which has also got some sorting in there. But of course, if it's sorted, you can use a binary search, and a binary search has got a O log n, I think, big O of log n. And then the last one is it's not the last one, but the next one is the dictionary thing. Now, in the dictionary, there are two ways to look for. For me, the real world use case of a dictionary is where you have to say, does it contain, and then return the value. You can't just blindly return the value. Sometimes you can, most times you can't. So I've got two implementations, one that has just to look up directly, and the other one that uses a contains. So it's first seeing if it contains, and then it returns the same number. So that's like, it's kind of doing a lookup twice, right? But that's more of a real world case than the previous one here. So there's a lot of benchmarks that have occurred that have to happen here. As you can see, it's 1, 2, 3, 4, 5, 6 times 4 or 5, right? So that's 30 benchmarks. So, but I'm sure you want to look at the result, right? So let's look at the result. Let me see if I have the output already there. Well, what do you know? I got it. It's not a nice color. Sorry, don't have it. Okay, I'm going to have to run this and then get back to you on the output. So hang in there. I'll be right back. I couldn't wait that long. So I have a graph that I already built for the different benchmarks on that test. So I'm going to show you that. So what I have here on the x-axis is the number of elements. Of course, I started with lower ones. So because we only had like, I think it was 50 through or 60 through, whatever. But this is a larger set of values. You can see here for the value types. So when a value type is put into an array, which is a reference type, an array is actually faster than a dictionary for up to 30 elements. Did you know that? An array, which is an ON operation, is faster than a dictionary. This is just not even a sorted array. This is just the normal array, right? So if you don't know why, please take a look at that video I linked to earlier on performance, and you'll hopefully be able to answer the question for yourselves for that. Did it match up with what you put in the description in your comments below? Yes? No? Okay. Well, the next test is for reference type. Same idea, but instead of putting value types into an array, if you put a reference type in an array, which one's going to be faster? put your answers to that in the comments as well and see if it matches up with the actual result. But after 30, you can see that the dictionary is faster than the array is. And the sorted array, even though it's sorted, apparently, and doing a binary search is not as fast as the array itself, and slower than the dictionary. So the sorted array didn't quite work out. Now that could be in implementation detail, but it's also because of the fact probably that it's calling callback methods to do the sorting, and method calls are slow. And so that's costing us something there. And of course, the dictionary without the contains is slower here, and it becomes faster at about 20 elements. But the real world scenario is that the array is still faster for 30 elements. And then after 30 elements, 35 and on, the dictionary, even with the contains, is faster than the array. And you can tell from these numbers here, these two numbers, that the contains is almost taking twice as much time as the one without the contains. In other words, contains is doing a search twice, right? Does it contain? And if it does, then give me back the value. So you can also, I think there's also like a try get on dictionaries. And maybe that's a better way to do that. But you know, in production scenarios, you do a try get. So it's trying and getting at the same time. And if it doesn't, it says null. So that might be, that'll save you the hit. All right. So the results have been, of course, determined using BenchmarkDotNet. The next one is reference types in a dictionary. The other thing you're going to notice here is at certain points, there seems to be in all the graphs a bit of a kind of hitch or a glitch, right? Here, and then again over here. Can you explain that? Again, the video, I never knew that those videos are going to be so correlated to the benchmarking side, but every time I'm thinking about something, I said, yeah, that's been indirectly been explained in those videos. If you want to try and get an explanation for that, take a look at that video and you'll hopefully be able to answer that question as well. Okay, the next one is the reference types array. And you can see here that the dictionary is it's a constant time. So it's truly constant in this case, whereas over here, it wasn't quite constant, right? It was increasing, even though marginally. It didn't appear to be a constant. The gray is the dictionary and the contains. They both get that little glitch here at this point. Now for the one that is reference types, it's fairly constant. But if you look at the array, which is blue, it's not bad. I mean, it's an ON and the N is only 80. So for, 80, 100 elements, you're not going to see a whole lot of difference there. So you're talking about, this is in nanoseconds, right? So that's 10,000 nanoseconds. So that's, I guess, 10 microseconds. So that's about 20 microseconds. I mean, does that make a difference? Now, if you would look at the memory utilization, you would find that the dictionary uses up more memory than the array does. So again, as I said, there's this tension between performance and memory. And maybe in some situations, you have to pick an array just because the array is a little more efficient in regards to memory and dictionaries are not. And you can see with regards to, in this case, the reference type has a class. The class has a name and we are searching for the name. And so it's a string compare. And so I've also added things like string compare ordinal and string compare ordinal ignore case. And so you can see that the ordinal ignore case was the slowest. Really. This was surprising to me because I've seen so many Stack Overflow and documentation recommendations always use ignore case because it's faster, because it doesn't have to, it's doing an ordinal compare. It's not based on ASCII or whatever the culture may be. And so ordinals are always faster. But if you look at just the ordinal compare here, which is the gray, it's not any faster than the normal compare, right? Which is this, or the dictionary. But these are not so different. The sorted array here is neck and neck with the non-sorted. So again, there's no real benefit to the sorted array. And of course, if the sorting itself is outside of the benchmarking itself, the amount of time it takes to sort. So that's another thing to consider here. Maybe that's not a valid case for you to test if you have to sort first and then do the job. But you skip the sorting part as the sorting itself outside of your benchmarking, then it's not a valid test. In my case, I was not trying to benchmark the sorting itself. All right. So the next thing we have here in our benchmarking program is the string equality. How many ways are there to compare or equate strings in .NET? Okay, think about that. Keep it in your head and I'll tell you the answer. There's quite a few actually. So we have a bunch of different methods here. We've got the equals operator like we did before, except this is parameterized as you can see here, but this string also is a random in terms of the length of the string as well as the content, right? So I've got the randomizer to get me a string, and then for the string B, I'm just adding some other ASCII character here to make sure they're not equal. And it's parameterized from 10 elements, the length of the string, to 100 characters and so on. I did a bunch of other tests, but didn't have much of a difference on, so I've just commented out those. But in the report I'll show you, you'll see the actual numbers. So that's the string equals operator, the equals method, the ordinal ignore case, ordinal compare, and then the ordinal ignore case, then the invariant culture ignore case, and then the equals method with the ordinal. So there's a string comparer class as we have them in .NET. You can use those classes and you can set up how do you want to compare using ordinal or ordinal ignore case. So that's what I've used there, and so on and so forth. So there's a bunch of different, of course you can imagine this test would take a long time to run, so I'm not going to run that at all. I'll show you the report I have on it from before. So between 10 elements in an array to 1,000 elements in an array, the equals method and the equals operator are sort of neck and neck, as you can see. They're overlaying each other here. So there's no difference between equals method and equals operator, and the length of the string didn't make a difference. The string compare ordinal is almost as fast as those two, right? So you're talking, this is again in nanoseconds, so you're talking about like 2 and like 1 point something and 2, right? 1.45, and ordinal compare 1.7, so there's not a big difference between those two. But then these three on the top here, it's funny how 3 came down here and 3 went up there. Vast difference between these three, which is the equals ordinal compare, the equals ordinal ignore case, and the string compare ordinal ignore case, right? Remember, I'm going to make all of these projects available to you. And the link will be in the show notes below. This will be on my GitHub, so you can take a look at this project from there and kind of dissect it yourselves. And if you feel like running the test yourselves on your hardware, do that to see how that compares with the reports. And the Excel spreadsheet is part of the download as well, so you can get a look at that. Next up is string concatenation. So, and this is another, interesting benchmark to do just to see, how right or wrong you are in your assumptions. So from a concatenation perspective, there's different ways to concatenate, or different ways I've decided to concatenate. So I'll skip through all of this, but the string length can also be parameterized. I've not done that. I probably removed it at some point. But essentially I'm saying I'm going to concatenate using the plus operator. Now we've always been told not to concatenate using the plus operator, have we not? Use a string builder. In fact, here, I remember, I'm sure I'm going to get a squiggle somewhere. Yep, there it is. So it says use a string builder instead. So is a string builder faster than the plus operator for strings? Write your answer down in the comments and then check your results here. But compared to all the other stuff, so I'll show you all the other concats and you tell me which one you think is going to be the fastest and or the slowest, right? So one is with the plus operator, and I'm simply adding the plus like that up to 10. The next one is with the plus operator in a loop, so I'm concatenating them in a loop with the plus operator. Then is the concat method. The concat method has up to, I think, 4 overloads. So, well, 3 overloads with 4 arguments. And for the next one, I'm just concatenating from the previous concat and so on. Then concatenating a loop using the concat method. The concat method in C#, the string concat, is actually not even implemented in C#. If I remember correctly, it's implemented. So it makes an external call in the, if you look at the source code, and then it calls into a C or C++ routine. So it's highly optimized. Hint, hint. String builder. So I'm using the string builder here to concatenate up to 10. And then I do a string builder in a loop. And then I do a string.join. So which one is going to be the fastest and which one's going to be the slowest, do you think? And of course, it's going to probably change with the numbers. Okay, write those things down, pause the video, put in your comments, replay the video and see the result. So here's the result. So we have the gray, which is the concat method, is the fastest. What did I tell you? Hint, hint. Actually, I don't remember the results, but I just know it from my own experiences. So I don't actually remember the results. This thing was written almost a year ago. All this stuff was done about a year ago. So I don't actually remember all the outcome of this. But concatenate is the fast, and it doesn't matter how large this number of 50 character strings being concatenated. So it's 50, that's 50, 50, and that's 50, 50, 50, and so on. So this number of 50 character strings. So it's a fairly large string being concatenated, and I picked 50 because I just thought that it needs to be a large enough number to make a difference in terms of some sort of performance hit. You'll notice again, we get these bumps here. See this hump here, this dip there, dip here, bump here, dip there, at a very specific point here, and then again here. It's sort of the same thing. This is almost like there's an imaginary vertical line here at 9 and then at 8. Why is that? Extra brownie points for anyone that can answer that question, but you're gonna have to take a look at my other videos, hopefully, to be able to answer this question. It's not specifically called out there, but I hint at some of the things that might be occurring. But I talk about some of the things that happen at a hardware level, and that might give you a hint as to what might be occurring here, and that might explain that. Those humps, the dips and the peaks there at certain times. It seems to be everywhere, right? There's a thing, dip and a hump here, and dip and a hump here, and so on. All right, so the slowest one seems to be, I guess, this yellow as the numbers go up. So they're kind of neck and neck here, yellow and orange. So there's the plus operator in a loop with the plus operator. This is the blue, actually. There's a plus operator. Look at the plus operator. Look at that. I mean, that is not bad at all, right? So why is all the hullabaloo about you don't use the plus operator? I mean, seriously, guys. When you start believing things that people say without testing for yourselves, hang on there. You're not seeing the memory allocations and the pressure on the GC by using the plus operator. Listen, if you want to do designing or you want to design benchmarks, not only is that difficult, understanding the results and what else to test for or check for is really important. The plus operator is fast, but it's causing a lot of garbage. That garbage is going to have to be collected, and that garbage collection is going to kill you in a large system. Testing benchmarks in isolation is okay as long as you understand that they may or may not be may or may not be reflecting the real world scenarios. You're testing one method here that eventually gets deployed to a production system with hundreds of thousands of methods. You cannot discount things like memory, things like CPU utilization by other processes and stuff like that might occur that slows things down or alters your readings. So even though here in the one-off, you're seeing the plus and the string builder is nowhere near. Look at the string builder here. There's the green, which is a string builder. There's a light blue, which is a string builder. So these two, it is nowhere near the plus operators, right? And the string join, look at the string join. Look at that. It's like pretty, almost like a steady, it's a linear. Both of them are almost, except these two are neck and neck here. My recommendation would be use the plus operator for a few strings. So if you want to concatenate 4 strings, you can use the plus at compile time. If you remember my C# loading video, I think I talk about that. At compile time, that concatenation will convert to a string.concat method call, And streamline method concat is super fast, and so you'll get the benefit of doing that. So don't jump to using a string builder for small number of strings. Certainly if you're doing a loop and you don't know the loop is unbounded, maybe it's not like a fixed number. Today is 10, it could be 1,000 in production. You need to use a string builder. But if you're doing like a 2-string method implementation of an object that has 4 properties on it, just concat, right? It's way faster. Less memory overhead as well. So it's not so much about the speed. Remember, there's this tension between memory and performance. And sometimes you get both without sacrificing the other, meaning less memory still gives you better performance. But sometimes you're going to get more performance by adding on more memory, and you need to get that balance, and you need to understand that. The memory diagnoser will actually help you understand memory allocation and stuff of that nature. So when you get the source code, run the one that does the string concat, and look at the memory diagnostics, look at the garbage collections, and the amount of memory allocated and how many garbage collections occurred per 1,000 iterations. And that'll give you that clue. Anyway, I'm going to skip the rest of them. I'll probably make another video on these two. I think they're also important. It's nice to do. And especially this slug producer one I talked about earlier is a good unit testing exercise. So maybe I can use that to give you guys a unit test exercise for that, to do the slug producer as a unit test, or write a unit test for the slug producer. And then you can use the different implementations to ensure that the implementations are correct, because all the unit tests are passing. I hope this has been a useful exercise for you. You've learned some things, and I've not bored the heck out of you, which I tend to do sometimes when I'm talking on a serious topic. But yeah. So if you like this video, please give me a thumbs up. If you're not a subscriber and you reach so far, you just have to subscribe. If you reach so far, it doesn't matter. Even if you subscribe before, subscribe again. It might not be harmful. And hit that notify button also. And I will see you next time.